We're going to continue our discussion of acids and bases by talking about pH and pOH. So before we talk about pH and pOH, we want to talk about the autoionization of water and the ion product constant. So in the last video, we talked about the fact that water was amphoteric. It could act like an acid or a base. And it turns out, even in pure water, water will react with itself, where one water molecule acts like an acid, another one acts like a base, and so one water molecule donates a proton, that is an H+, to another water molecule, creating hydronium and hydroxide ions. And we can write the equilibrium constant expression for this reaction. On the reactant side, the water is liquid and liquid, so that won't appear, but we've got aqueous H3O+ and aqueous OH-, so that will appear. And so then when we write the equilibrium constant expression, we'll get the concentrations of the products, the H3O+ and OH- divided by 1 because we've got liquids in both of the reactants. And so this is a very special equilibrium constant expression, so we give it its own symbol, and we call this Kw. And this is sometimes called the ion product constant or the autoionization constant. And it changes with temperature, but for the most part, when we do calculations, we use Kw as 1.0 times 10 to the minus 14. And so this means that the hydronium ion and the hydroxide ion concentrations in any sample are always linked. And the product of H3O+ and OH- is always equal to this 1.0 times 10 to the minus 14. And so the consequence of that is it's kind of like a seesaw. If one of these goes up, the other one has to go down. So if I have a lower concentration of H3O+ as I do in this picture, that means that I'm going to have a greater concentration of OH-. But we could tilt it the other way or in any direction, right? The more I have of hydronium ions, or the less I have of hydronium ions, then the more or less I have of the hydroxide ions. All right, so I think most people are at least a little bit familiar with the concept of pH. But the p function is just an algebraic function, and we can apply the p function to anything. It just means take the negative log base 10 of something, whatever it is. And it's a useful way to express the concentration of hydronium or H+ ions. So the pH is just the negative log of the H+ concentration. Or more formally, as we talked about in the last video, we don't really have H+ in solution. We really have H3O+, but we often use the two interchangeably. And the reason we like pH is because like the concentrations of H+ or H3O+ are often going to be things like 5 times 10 to the minus 6 or 1 times 10 to the minus 4. But in the pH, 1 times 10 to the minus 4 is just 4. Right, so it's just an easier thing to work with when we want to talk about what is the concentration of H+ or H3O+. But as I said a minute ago, right, we can do a p function of anything, and it just means take the log base 10. So the pOH is just the negative log of the OH- concentration. And I guess maybe we should have mentioned, when you just say log, it's understood to be log base 10. So going forward in this course, we'll almost never write log base 10, right? We'll just write log, and then it's understood that the base is 10. All right, so let's talk about the pH scale. So you've probably seen this before, but when pH is equal to 7, a solution is considered neutral. We don't consider it acidic or basic. And what happens at pH 7 is the H3O+ is equal to OH-. And it turns out at that pH, they're both equal to 1 times 10 to the minus 7, right? Because if they're both 1 times 10 to the minus 7, then when I multiply them by each other, I'll get 1 times 10 to the minus 14, which is Kw, which is what the product of H3O+ and OH- has to be. And so, again, when the pH is 7, we consider that solution to be neutral because the hydronium and hydroxide ion concentrations are equal to each other. That's sort of the middle of the pH scale. When the concentration of H+ of hydronium ion increases, then we say the solution becomes acidic. If the concentration of H3O+ decreases from 10 to the minus 7, so that means the hydroxide ion concentration is increasing, then we consider that solution to be basic. And so when pHs are higher than 7, we have a basic solution. When we have pHs below 7, we have an acidic solution. And so just to sort of put this into context, we have some common compounds here. So pure distilled water would have a pH of 7. It would be considered neutral. Milk is slightly acidic. Things like vinegar, lemon juice, or stomach acid are quite a bit more acidic. Or if we had 1 molar of the strong acid HCl, that would be a pH of 0. Now, the pH doesn't stop at 0. We can have strong acids that are more concentrated than 1 molar, and so the pH scale can actually go negative when we have concentrated strong acids. And then when the pH is above 7, we consider the solution to be basic. Blood is slightly basic. Ammonia is a popular household cleaner. Windex is a common window cleaner. And if you ever use Windex, the smell that you associate with Windex, that is due to the ammonia that's in the Windex. And that's a relatively basic solution. If we have 1 molar of a strong base like sodium hydroxide, that would be a pH of 14. But again, the pH scale doesn't stop at 14. If I had more concentrated NaOH than 1 molar, then the pH would actually go above 14. All right, now, a couple slides ago, we gave the equation for how do you get the pH if you have the H plus or the H3O plus concentration. If we can go in one direction, then we can obviously go in the other. So if I have the pH and I want to know the H3O plus, then the way we would get that is H3O plus. To get that, we would do 10 to the minus pH. Or conversely, we can do the same thing with the hydroxide ion concentration. If I want the OH minus concentration and I know the pOH, then I can do 10 to the minus pOH. All right, and another useful formula that we have, if we take our Kw expression, right, so H3O plus times OH minus is 1 times 10 to the minus 14, and I take the negative log base 10 of both sides, then we can actually derive another really useful equation, and that is that pH plus pOH for any solution is always equal to 14. So what I want to do to finish this slide is let's make a list or a chart of all of the useful equations that we've been introduced to in this video. And so you might want to take a screenshot of this, or if you're in my class, I'll take this and I'll post a PDF of this to our course site. But we can see, so we can go back and forth between for any given solution, we can go back and forth between the pH, the pOH, the H3O plus, or the OH minus using the equations that we've talked about. So if I have a particular solution and I know the pOH, or I'm sorry, if I know the pH and I want to know the pOH, or vice versa, I can always use this equation to go back and forth. So for any specific solution, the pH plus the pOH is always equal to 14. Or if I was dealing with the H3O plus and OH minus concentrations, I can always use that Kw expression. If I know the OH, I always know the H3O plus and vice versa because they're linked by this equation. And then if I have the H3O plus and I want to find the pH, I can always go this way. So pH is minus the log of H3O plus. Or we just saw in the previous slide, I can go in the other direction. If I have the pH, I can find the H3O plus by using this expression. And then we have the same relationships for OH minus and pOH. So all of these are always connected. And if I know any one of them for a given solution, then I can always use the equations that we have here to calculate any one of the other ones. And then, there's often, more than one way to go, right? If you give me the pOH and I want to know the H3O plus, well, then I could go down in this direction or I could go across here. So there are lots of ways that we can use all of these equations. And so in the next video, we'll look at some examples of using these equations to do some calculations.